Hi, my name is Julia, and today I will present our work Heatmap-based out-of-distribution detection. First, I will start with the problem definition. So we have a classifier f that is trained on the dataset dn, sampled from the distribution pn. This is our training distribution. On the right side, I have an example from Tiny ImageNet. This could be our in-distribution training dataset. During inference, the classifier is fixed. The classifier can now be exposed to samples from the training distribution, but also to samples that are from a different distribution P out, which is different from the training distribution. The predictions of the neural network are unreliable for those out-of-distribution samples. Therefore, we want to detect the out-of-distribution samples. Now, in our approach, during training, we assume access to in and out of distribution training data. We keep the classifier fixed, but we train a second model to predict heat maps. So we have an example from out of distribution data on the right side, which could be places 365. So clearly you can see that the samples are different to the in-distribution data. They either are from a different class or have a semantic shift. So now it's important to note that the out-of-distribution test data, which we later use in our evaluation, is different to the out-of-distribution training data. So the out-of-distribution training data could be sampled randomly. In our approach, we do out-of-distribution detection based on heat maps. So the first step is to define the heat maps. For in-distribution training data, the heat map is defined as zero-response heat map. For out-of-distribution samples, we want a responsive heat map. Therefore, we define the heat map as normalized difference from the image to the closest in-distribution training image. The closest in-distribution training image is searched for in the feature space of the classifier. In the feature space of the classifier, we look for the closest in-distribution training image with the same class label as the class prediction for the out-of-distribution image. And then we take the minimum Euclidean distance. When we found the closest in-distribution training image, we take the normalized difference in the image space. And this is our expected out-of-distribution heat map, which we later use for training a decoder. Now that we defined the heat maps for in and out-of-distribution training samples, we train a decoder based on the features and the class prediction of the classifier. The classifier is fixed and only the decoder is trained. So the decoder is trained to predict zero-responsive heat maps for in-distribution data and responsive heat maps for out-of-distribution data, which are the normalized difference to the closest in-distribution training sample. Then, during inference, both models are fixed. And the out-of-distribution detection score is based on the heat map. The out-of-distribution detection score is defined as the average over the maximum heat map values. If the score is smaller than a threshold, we have an in-distribution samples. Otherwise, we have an out-of-distribution sample. In this slide, I have visual results of heatmap predictions. The heatmap predictions are for ResNet 50 trained on Tiny ImageNet. So on the left side, we have an example test image from Tiny ImageNet, where we have a zero-responsive heat map. Then we have out-of-distribution test samples from Textures, Sun, and iNaturalist. In all three cases, we have responsive heat maps, which show that we have out-of-distribution samples. This was a short introduction to our work, and on this slide you can find my contact information and the link to our GitHub repository.